This is NMR Spectroscopy Lecture 2. In this lecture, we will discuss that how we can identify and analyze organic molecules in the NMR spectroscopy. NMR spectroscopy is based upon a nuclear spin of proton, carbon 13, nitrogen 15, and so on. Let's discuss the structure of an organic molecule like ethyl benzoate. Then we will see the proton and carbon 13 NMR spectrum of that molecule. This is the structure of the ethyl benzoate. Ethyl benzoate has an ester group and it has the double bond in the benzene ring. So double bond is also a functional group. You know that we can identify these functional groups in the IR spectroscopy, but what is the new in the NMR spectroscopy? What are the benefits of NMR spectroscopy? So let's discuss them. In the NMR spectroscopy, we can identify that there is a benzene ring in the molecule which is monosubstituted. Like we can even identify that we have a benzene ring, but it is attached to only one moiety. And we can also identify that in the proton NMR, we can identify that how many protons are there. In the carbon 13 NMR, we can identify that how many carbons are there. We can also identify that how many protons are present around the CH3 group, how many protons are present around the CH2 group. Like there are 2 protons are present in the neighborhood of CH3 group. 2 protons are present in the neighborhood of CH3 group, and 3 protons are present in the neighborhood of CH2 group. We can also identify that how many types of carbons. In the carbon 13 NMR, we can identify that how many carbons are there, how many different types of carbons are there. Like some in some cases we don't have the different types of carbon, as we can see that there are 3 protons which are attached to the same carbon. So these 3 protons have the same chemical environment. So like these 2 protons are attached to the same carbon, so these 2 protons have the same chemical environment. So we will discuss this in the next lecture or the next slide, so that how these signals will appear in the proton or carbon 13 NMR spectrum. And this is a table of shift for the proton NMR, and we get the values from 0 to 12 in the proton NMR spectrum. The proton which is present in the CH3 group will give us a value, will give us a peak from 0 to 4, and the one which is present in the CH2 group or in the CH group will give us a value from 2 to 5. So every proton which is present in a different chemical environment will give a different value. The one which is attached to the double bond carbon will give us a value from 4 to 9, and the one which is present in the alcohol will have a large range. The one that have a large range, it is difficult to identify that it is related to which group, because there are many that are coming in the same range. So the one which is present in the SH group have the range from I think 2 to 5, and the proton which is present in the carboxylate acid group, it has the larger chemical shift than the other ones. It has the shift from 10 to 12. And then one which is present in the NH and NH2 have the chemical shift from 0 to 5. So every time when you see the NMR spectrum, please keep this table, so you can identify, you can look at that table, that where is my peak and what would be the chemical shift of that peak, and this peak of which group. Like there is a CH3 group, so its peak CH3 group, so its peak will appear from 0 to 4, and the CH2 group peak will appear from 1 to 5. So there are also protons here in the benzene ring. There are 5 protons, and the protons which are around the aromatic ring has the chemical shift value of 7 to 8. So we can easily identify that this proton is in the aromatic ring, or it is on the aliphatic carbon. So from the proton NMR spectrum, the advantage of this spectrum is that we can identify that there is a aromatic ring or not. So this is a proton NMR spectrum of the ethyl benzoate, and we almost get let's take a rough idea that we 1 2 3 4 5, we get a 5 peaks. There is a cluster of peaks, so it is difficult to identify them. So these peaks, the first 2 peaks are very clear. One is above the 1 and the other is above 4. So there are almost 10 protons. There are 10 protons, and this is a triplet and this is a quartet. Triplet mean there are 3 peaks, 1 2 3. There is a 1 peak, but it has 3 subunits, and this is a quartet. Mean there is a 1 peak, but it has 4 subunits. So we have seen previous in the table of shifts that the proton which are attached to the aromatic ring has the chemical shift values above the 7. So we can easily identify that these are those protons which has the chemical shift values above 7. So these are the aromatic protons. So in the it is difficult to resolve the proton spectrum of the benzene, these aromatic protons. We can most of the times we can't differentiate the peaks, that this is the peak of this proton, this proton, this proton, this proton. So it is difficult. But these CH3 group, like these protons peaks and this protons peaks, are easily to identify. So CH3 group has less chemical shift than the CH2 group. We have seen in the table of shifts that CH3 has the less chemical shift. So this first one is the peak of the CH3 protons. So there are 3 protons, but there is only 1 peak for the 3 protons. Why? Because these 3 protons are in the same chemical environment. These 3 protons are attached to the same carbon, so there is only 1 peak will be appear for them. Like this is a we can say that this is a proton A, this is also A, this is also A. So these 3 protons are same, these are attached to the same carbon, but these protons on the second carbon CH2, these two protons are also same chemical environment, and one that is near to the carbonyl group on the aromatic moiety, like on the benzene ring. This is a proton C. We can give any number to these protons. You can give number or letter identification to these protons. This is just for the easiness, like this is a proton C. These two protons are on the same chemical environment because these have the same distance from the carbonyl carbon. Like they are only on the second carbon. Like this is the first carbon of the carbonyl, and this is the second carbon. And these protons are D because these are on the 2 carbon distance from the carbonyl carbon, and this is proton E. So there are how many protons? 1, 2, 3, 4, and 5. There are 5 different types of the proton in our structure. So the first step is to identify that how many different types of protons in our chemical structure. So the first peak will give us a triplet. Why there is a triplet? Because triplet tells us that how many protons in the neighborhood. Like this is a CH3 group. We will not see that how many protons on our CH3 group, but we will see that how many protons are in presence of neighborhood of HA proton. So you can look at any HA proton and look at the neighborhood. There are only 2 protons in the neighborhood, HB and HB. There are only 2 protons, this one, this one. So there are 2 protons and we will add 1 into them, and it is equal to 3, means it will give us a triplet. We will always add 1. So this peak will appear in the NMR spectrum. So on the second one, let's discuss the peak of the HB proton. HB proton is this peak of the HB proton, and you will not look at these HB protons, but you will look at the neighborhood of these HB proton, that how many protons are present in the neighborhood. So there are 1, 2, 3 protons are present in the neighborhood, and 3 plus 1, 4. So it will give us a quartet. So you have to add 1, always add 1 in the number of protons. And this is this peak is not represent the triplet will not represent that how many protons are H's, but it represents that how many protons are present in the neighborhood of H. So always remember this. And whenever you see that there is a cluster of the peaks after the 7 ppm, ppm is a parts per million, and these are the chemical shift values. And we take the tetramethylsilane as our reference compound. This is a covalent bond, tetramethylsilane as a reference compound in NMR spectroscopy. When we change our atom, like we will go to the phosphorus or the nitrogen, we often change the reference compound, but in the proton spectrum we use this tetramethylsilane. So if you forget this, then you can repeat the video and look at that how I resolved these peaks. So let's discuss the carbon 13 NMR spectrum of ethyl benzoate. And this is a carbon 13 NMR spectrum. I already draw this molecule to save time. And how many peaks are there? 1, 2, 3, 4, and this is a small peak. 5, 6, 7, I think. Let's see that how many peaks are there. This is uh, there is a CH3 group, so this is first carbon. So CH2, this is a second carbon. So carbonyl carbon is a third carbon, and the one that is attached to the carbonyl carbon, this is a fourth carbon. And these two are carbon number 5, and these two are the carbon number 6, and this is the carbon number 7. So there are the 7 different types of the carbon. So these two are the same carbon number 5, because they are the same distance from the carbonyl carbon, and 6 are at the same distance from the carbonyl carbon. And let's look at that, the first peak. This is I will not discuss the multiplicity of these peaks. This is triplet, doublet, quadruplet. We will discuss them in the next video. So let's look at, this is a CH3 carbon or CH2 carbon. You always know that CH3 carbon will appear first, so this is a signal of CH3 carbon, and this is a signal of the CH2 carbon. So you can easily identify that which one of the CH3 and which one of the CH2. So the important thing I want to tell you that the carbonyl carbon, so carbonyl carbon will appear ester. Oh, there is a mistake, that this is the ester molecule. So single bond O, yeah, there is an O group. This is ethyl benzoate. So ester group carbon will appear after the 160 to 180. So like there was a mistake in my molecule, that because the carbonyl shift is higher than that, so I have identified from the spectrum that there is a mistake in the molecule. I have not written the 1O, so there is an ester group. So this is the ester group peak, and there are 7 different peaks, and mean there are 7 different types of the carbon in our molecule. And why these two peaks are higher, and why these peaks have the almost the same height. These 1 almost have the same height, but these two have the double height, because there are two different types of carbon that have the same chemical environment, like this one, 5th and 5th, and 6 and 6. So when the carbon will increase, then this peak height will increase. If there are 3 carbon, then the peak height will increase. If there are 4 carbons in the same chemical environment, then the peak height will increase more. So in the spectrum we can also identify that how many different types of carbons are there, and how many carbons have the same chemical environment. So I think it is enough for today. We will discuss many different aspects about the NMR spectroscopy in the next lecture. So if you like the video, please subscribe the channel. Thank you.